So, welcome everyone. I'm really pleased to be here. I must admit that I'm not from industry, not from business. I'm not in fashion, and I'm not a designer. I'm just a researcher at the very lower end of the chain of creation and innovation. Today I want to talk about things that you maybe do not even remember because you have not been born at that time. It goes back about 30 years, 21st of August in 1981, when technology was given to humanity, declared as being helping the individual, a one-to-one relationship between technology and individuals. To be personal, to be addressing all the individual personal needs that people have, and directly support the end user. The personal computer was born, and you see shapes of the kind everywhere today, still. But even 10 years later, there was an idea. It was created by Mark Weiser, Xerox PARC, Palo Alto Research Center. He was the research head there. And he published a paper, and the paper in its very beginning read that the most profound technologies are those that disappear, claiming that they would weave themselves into the fabric of everyday life until you cannot distinguish them anymore from everyday life. That was 20 years back. And today, maybe, since this is next and since this is a fashion event here, you approached, you took your sunglasses in the morning, your shoes and your belt and your watch, took your car, now you're sitting here on this chair, listening to the presentations. All this is seemingly low-tech, but not necessarily. There are two trends, I think, that have fertilized high-tech clothing. One is miniaturization, clearly. What can you build on one single square inch of silicon? Well, there is wireless communication, ultra-wideband, as you see here. You can do 1 gigabit of data transmission using this single chip here. You have quad-core technology onto a single CPU. On one single square inch of silicon, you have a geopositioning unit which gives you the position of wherever this is sticked on with a precision of 5 meters on the whole planet. And there is sensors, and sensors can capture everything about the environment. Humidity, temperature, noise, light level, acceleration, magnetic orientation, and so forth. And on the other hand, there is growth, the explosive growth of the internet, of the global network. This is just a sketch of how this internet has evolved over time and how it is still continuing to grow. And this growth is unlimited. We see the planet, we see the continents here, and we see this huge, huge, dense mesh of nodes, presumably now serving 7 billion people, but also serving them as they are doing their everyday things, their everyday tasks, their duties. So on planet, we have about 2 billion internet users, but we have already 5.3 billion mobile phone users, out of which about 1.1 billion are smartphone users. And they are part of this net. And they have all this internet technology together with the sensing technology integrated. And there is 10 million things about awaiting to be part of this net here. So if we rethink about how you came here and what you used to dress up today, we can look into more detail of what the potentials of technology are for the accessories that you have here. And this is not telling science fiction now, this is all technology that we have developed in our department. Everything that I tell you now is in existence. So one is this idea of having glasses that are enhanced with sensor technology, like digital cameras. They would capture what you see and they would give an interpretation of what you see. There is a geopositioning unit which would tell you where the thing is. It would have a digital compass. It would tell you where you're looking at. And combining this with the internet via wireless communication technologies, it would relate the situation to what you understand, even to your expectation and to your experience, what you are seeing. And it will explain you in more detail what is belonging to that situation. So it could help you in several situations of your life by capturing the scene, but also by trying to understand the scene, and you would be given instruction through your ears and through your eyes. On the inside of these glasses, we have a little display, and it would tell you what is an augmentation to that situation that you see, that you perceive. So that was the vision, and here is the evolution of the process and how we built it. There is this challenge of putting a display on the inside of the sunglasses. This is very crucial because of the anatomy of the human eye. So you have to be very tricky in order to perceive images that are that close to your retinal focus. We managed to do it. We managed to integrate all the electronics into a very miniaturized platform. So there is a high-performance computer integrated in it. There is wireless communication. There is a display controller. There is barcode scanners. There are several sensors that go from position sensing even to your stress level sensing by galvanic skin conductance sensors, which are, of course, an indication about your stress level that you have. So depending on your mood, these glasses would tell you something about what you're experiencing. Let's have a look into
spectacles.
Into the system.
Technology seamlessly woven into the fabric of an everyday object, enhancing the service capabilities of simple sunglasses to a high-tech, wirelessly connected, internet-enabled, mixed reality, multimedia system for everyone. Spectacles integrates accelerometers, gyroscopes, a compass, a microcamera, a laser scanner, a micro-optical display, a microphone, a text-to-speech and voice-to-text unit, wireless communication stacks, and biosensors like EKG or blood oxygen sensors into an autonomous, wearable computing system. Physically, the spectacles components are embedded into an eyeglasses frame and a companion unit worn on the upper arm. The most crucial part of spectacles is the embedding of a micro-optical display on the inside of the eyeglasses frame. A QVGA display mirror system is used to deliver multimedia content directly into the wearer's eye. A center frame accelerometer system traces head gestures and interprets them as user input commands. The companion unit comprises a laser scanner for barcode recognition and application-sensitive buttons for direct user interaction with the spectacle system. Inside, the companion hosts a powerful X-scale microprocessor system with a barcode reader and micro-optical display electronics, a GPS and compass module, as well as the power supply unit. The spectacle system has been designed for and empirically tested in a variety of real-life scenarios, ranging from outdoor sports activities to tourism applications and shopping situations, as well as surgery and emergency scenarios. The modular hardware assembly and automated software component configuration of a spectacle system is demonstrated with sports spectacles. Here, the compass and GPS module, together with a heart rate monitor, are embedded to support the specific service needs of mountain biking, as an example. Sensitive to the planned biking route and the biker's vital condition, the sports spectacles display shows trail ascents and descents, cardinal directions like north, east, west, and south, approaching waypoints, and the heart rate. The context awareness of the services, implemented in software, lets the display content automatically adapt to a particular situation. Here, a waypoint with a trail junction is approached, and the display automatically switches from profile mode to map mode, allowing the athletes to follow the right trail without stopping, or any other explicit user interaction. Here we have the leisure spectacles, assembled, configured, and service optimized for tourism applications. The GPS and compass module, together with the accelerometer integrated into the eyeglasses frame, allow for the real world to be browsed merely through movement, body postures, and head gestures. The sightseeing experience of a tourist, for example, is enhanced, delivering multimedia content right to the place, perspective, and angle of view of the spectator. The embedded position and orientation sensors allow the spectator's position to be related to the position of surrounding points of interest in geoinformation systems residing in the Internet, and make it possible to retrieve information according to the spectator's field of vision, but also according to his expressed areas of interest, preferences, even recorded experiences, habits, and learned findings. Browsing is controlled via intuitive triggers. Just changes in place or field of vision change the displayed content. Merely nodding or shaking one's head approves or rejects the displayed content. To enhance shopping experiences, the dietary companion spectacles employ a barcode scanner and code resolver via product databases. Here, nutrition information about grocery store products is retrieved from trusted servers through the Internet and displayed in a very pointed yet convenient graphical metaphor, a color-coded recommended daily dose percentage bar split into carbohydrates, fat and fiber, and calories, of course. Again, the interaction is intuitive. The respected product is presented to the barcode scanner built into the spectacle's companion unit, and the corresponding nutrition facts flash up in the display. A recommendation system relating product facts to personal preferences, habits, and experiences can make suggestions or express dietary warnings, depending on the personalization of the system. Surgery spectacles are yet another system configuration. Respiration and blood oxygen level are the most indicative vital signs of a patient in surgery. For a surgeon, it is thus essential to be informed about these parameters at any point in time during surgery. The surgery spectacles configuration integrates an open wireless communication interface to access sensor systems in the vicinity of the protective eyeglasses. In the example here, the surgeon is wearing the spectacle system, which wirelessly connects to the equipment in the operating theater.
So I think you got a message here about the potentials of such a system and how it can adapt to the situative context where it is being used. And I think you have an imagination of what else are the potentials of such a situated, personalized, and adaptive to the individual use case kind of technology. The very important, the very essential thing here is that it still appears and views and feels like an ordinary object of our everyday life. Let me at the end also go into more considerations about the other things that we addressed already. One is the shoes. We heard much about shoes. Here is a prototype of a shoe system for activity recognition that we have built. We have integrated into two shoes, two different categories of sensors, accelerometers and magnetometers, together with gyroscopes, so that using those shoes, based on the movements of your feet and based on the measurements from the sensors with respect to acceleration, yaw, pitch, roll, etc., we are able to identify the usual things that you express in your body movement. So we know from people that just walk along a straight alley, based on the type of sensor data that we collect and based on the machine learning technology that is behind it, in real time, what kind of gait this person is doing. So climbing upstairs has a very different shape, turning to the left, turning to the right, going low speed, going high speed. Standing, sitting are all the categories of activities that we can trace. And we have been using this activity recognition system, for example, to control the home electronics. All electronics in your home that are in standby mode can be controlled depending on your presence and depending on the activities that you exhibit. So the coffee machine does not need to be in standby while you're not here, and so does the TV set. But once you're approaching, things can be getting ready for operation. The belt has been an inspiration for a project that we have been executing for the European Commission. It is motivated by the perception that humans have in exceptional situations. Maybe some of you remember this skiing resort disaster in Austria in November 11, 2000, when about 162 people approached a train to bring them to the skiing slopes. And unfortunately, when the train approached the tunnel, an unattended radiator caught fire and the whole thing escalated. The disaster was that wind was drawn from the low-level exit of that tunnel, and it blew up smog and toxic gases to the upper part of that tunnel. People in this situation tried to escape by climbing upwards to that tunnel and were caught by these toxic gases. So about 152 people died due to the fact that they were trying to escape upwards, whereas 12 people who tried to escape downwards were rescued. So although they could have known what the right exit is, they did not choose it. One indication for that is that in such situations, the visual perception does not really work. So visual signs are of no help. The auditory cues that are given through speakers does not work. In this situation where you have mental overload, there are still other channels that you could use to deliver that information. And there are other situations like the Duisburg disaster and the London 7/7 bombing where this could have helped. In our belt development, we call it a life belt. We have integrated tactile elements, vibrotactile elements, which would guide you in such a situation towards the right exit. So depending on which exit is the most efficient one, not the nearest one, the most efficient one in the sense to be able to escape, it would give you stimulation, it would give you vibration, and it would tell you where to go. It even has sensors to indicate where the obstacles are and where you can pass through. And we have been using this technology, for example, to understand the evacuation of a whole train station. 5,000 people in Linz main train station equipped with such a tool here in a simulation would tell us that the evacuation efficiency can be considerably increased. The time for evacuating people is about 30% lower than without this technology. Then you might say, well, but no one has this technology. There is not everyone equipped with such a life belt. And there it is interesting to see that even if a small proportion of people have this technology, we have this effect of herding, this mindless following. And here you see two simulations. The one is a situation where we have 2,000 people evacuating from this floor plan of the train station, but only 4% of them wearing the life belts. Whereas on the other side here you see 100% life belt directed evacuees. And if I just animate here, you see that the difference is not very much. They all here with 100% equipment, they go towards the right nearest exit. Even if we have 4% of people having this technology, this mindless following principle helps to even achieve a very, very close performance for evacuation in this case. We also investigate on cognitive load and what we can do about it in everyday life. Not in exceptional situations, but maybe just in everyday life in your primary task as you're living. So as a sort of an indication, we know that the amount of information that we perceive as humans with the visual channel is about 10 megabit per second. With the auditory, in addition, there is another megabit per second. Then there is the haptic, the olfactory, the gustatory channel, etc. All these together are about 12 megabit per second that we perceive. Not much of them is kept. Only 16 bits per second go into perceptive memory, a single bit per second into short-term memory, and so forth. So we were intrigued by the question, given an object of everyday use like your watch, we use the watch without attending to it while we do our computer work, while we drive cars, while we carry things, while we open doors. The watch is here, we do not attend to it. The question is, if we use this as a platform for notification, for subliminal tactile notification, what is the amount of information that we can get from it? What is the amount of information that we can perceive? So we know that humans are capable of doing multitasking to a certain extent. If the stimuli-response couplings are not involving the same channels. So if the primary task is a visual task and the response is a motor task, you see something and then you react as a primary task, say your office work. And there is a secondary task where the stimulus is tactile. You get a notification through a vibrating belt here. And you respond to it in a vocal way, then this is a perfect situation for doing multitasking as a human being. So we did this. We did experiments on this. We did an alphabet of signs that you can deliver as a tactile pattern to those vibristlets. And then we were putting people under load for the primary task. We put them into sort of a heavy stress situation, and then occasionally and at random points in time, we delivered information to them. And it turns out, depending on the low, moderate, and high level of load that we put on those people, the amount of information that can be captured occasionally and spontaneously is about a 3-bit information. 3-bit information means characters of 8 out of an alphabet of 8, if you want. So your mobile phone, if it is vibrating in your pocket, you know someone is calling. It's a single-bit information. It goes up onto 8-bit. You can map up to 8 different signs, like the Nasdaq is climbing, kids are good at school, the car is safe in the garage, whatever, and you would be able to perceive it. We also added information to the car key in the sense that we integrated a processor, a memory unit, an accelerometer, buttons to be directly interactive with the environment, and of course, you can put it into several different objects of your liking. This is the technology that's behind it. It's a mini computer, if you want, with wireless communication capabilities to the near environment. So in this case, we have experiments where the interaction with public displays is supported based on this technology that you wear. It's a totally anonymous, a totally abstracted from your individual and from your authenticity kind of information stored on this, and once you approach this public display, it would show you something that is exactly along your interest, along your profile, along the things that you want to see. More than that, it would follow you if you approach multiple of them. The way you go through this cascade of public displays, you would always be delivered with fresh information. Even steering could be implemented on this architecture, namely that those displays would guide you to the point where you want to go. Finally, we are also looking into this most precious resource that we think is there when designing system. This is attention. It is not the CPU power, it is not memory, it is not the communication bandwidth that you have. The most essential and crucial part of the whole story is attention. And what we investigated with the Sense Chair is that how can we assess for attention? We used 24 sensors, very thin, very small, into the seat and into the backrest of a chair. You won't feel them, they won't hurt, you just wouldn't feel them. You cannot decide from the fabric of a traditional chair and the sensor-plated chair. And once you sit down on this chair, your body is leaving a pressure pattern behind it, and those sensors would be able to analyze that pressure pattern. So one thing that we know is that the sitting bone distance is a biometric indication for individuals. So if the group of people is not a large one, then with high recognition rate, we can identify who has been sitting on that chair. Okay? We can even calculate the high pressure, mid pressure, low pressure areas of your pressure pattern. We can even check your weight and give alerts that the weight may be raised again, or you got down on your weight. The point is that the chair in itself would be able to identify you and do things like authentication to a computer system nearby, etc., automatically. So finally, we also looked into the dynamics of these pressure patterns, and we identified that from the body pose that you leave on a chair, we can estimate on the attention. As I look into this audience here, there are people which use the sit in this pressure pattern, and the back not at all. So they are attentive, they are leaning towards the speaker, me in this case, and I would classify them as attentive listeners to the audio, to the speaker. On the other hand, I do see body poses where people are very relaxed, maybe tired already here, and we could call this kind of person a relaxed person. Maybe it's asleep already, and we maybe need to change the style of presentation. So this is an example. We are approaching a world where we cannot attentively interact with computers anymore. So we are surrounded not with 7, but with 100, with 1,000 computers each and every day in our daily life. And we cannot attentively interact with them. So this is a change in the role of the interaction paradigm. Not we are giving input intentively and attentively and responding, getting response back in terms of output, but systems are observing, and they are trying to find what the right situation is, and depending on that assessment, give us the right services. Thank you very much.